So the recording has started. Thank you, Naya, for the reminder. All right, so I was just saying that I want you to mark your calendar for these two events. It's going to be really wonderful. It will be a chance for you to discuss with roboticists from all over the world, but all of them are African, people that have really advanced in their careers, both in academia or in industry and robotics around the world. You get a chance to interact with them, ask questions, and learn from their experience.
Donc, vous pouvez déjà actualiser vos calendriers afin de marquer ces dates importantes au bout desquelles vous rencontrerez des personnes importantes dans la robotique agriculture africaine.
All right, so we will be advertising this over the next week. We'll advertise it on social media. You can also invite friends. It's going to be an open event, so not only for PARC participants. It is primarily for PARC participants, but for anybody who is interested in robotics in Africa, we will be opening up to anybody. So not only those who are registered to participate in this competition.
Donc, le lien de la réunion sera disponible pour tout le monde, pas seulement les personnes qui participent à PARC. Donc, vous avez la possibilité d'inviter des personnes intéressées à la robotique agricole ou la robotique en général.
All right, very good, very good. So we will move on. I just wanted to give an overview of that. So we move on to part 2 of the Intro to Robotics workshop, okay? Andrea.
Donc, on va commencer la session.
So now the outline is that we will review the breakdown that we did for the robot, what are the sensors, and then we will wrap up the example 1. And if we have some extra time, we can look at an example 2 using GPS-based waypoint navigation.
Donc, pour la session d'aujourd'hui, on va faire un petit rappel sur les différentes parties de l'agriculture robotique. Et aussi, si vous avez des difficultés par rapport à l'exemple 2, vous pourrez vous rattraper sur l'exemple 1, vous pouvez rattraper sur l'exemple 2.
All right. So before I go on, I just want to get a sense of the room again to know if there are any persons, any teams, or any person here who is still having some challenge with getting their PC set up, meaning that you're not able to run Gazebo or ROS on your computer currently. So please, again, if you can just indicate yourself on the chat so that we can follow up with you after this workshop. Okay, so this is very important. If you are still having some challenge, please indicate in the chat.
Y aurait-il des personnes qui ont toujours des problèmes par rapport à la configuration de leur laptop? Si vous avez des problèmes avec Gazebo, ROS, etc. Vous pouvez écrire dans le chat.
All right. So please put it in the chat. You could also send a direct message to Andrea or myself if you prefer. But please, we want to identify you early so that we can try to support you as quickly as we can. Okay.
Donc, vous pouvez toujours envoyer un message privé sur Zoom à Andrea ou à Kenny et vous aurez des réponses
All right. All right, so we'll leave it at that, but please, I can see one comment. Thank you, personal comment. If you want to send a personal message to Andrea or myself, please go ahead. If you want to put it on the chat, we just want to make sure that we are recording, not recording, but we are taking notes of everybody who is having a challenge so we can support you well enough so that you can actually start running your software on your computer effectively.
Donc, nous voulons juste savoir quelles sont les personnes qui ont toujours des difficultés afin que vous puissiez avancer et plus efficacement dans la compétition.
All right, well, we'll move on. So last week in the workshop, we did an introduction to what is a robot, and we saw some examples of robots.
Donc, la semaine passée, nous avons fait un atelier sur l'introduction à la robotique et on a vu en quelque sorte qu'est-ce qu'un robot et quelques exemples de robots.
All right, and hopefully that was interesting for you to see. My main takeaway for you from that session, that part of what is a robot, is to expand your mind about what robotics entails. Okay, robotics is not just for humanoid robots, that's robots that look like humans. Robotics involves automation, autonomous systems, you can say, that can operate on their own and do things. Okay, so let me summarize that for the sake of Andrea. The main takeaway is that robots are not just humanoid type of robots, like I showed you in the pictures last week. Robotics really focuses on all types of autonomous systems.
Donc, la chose principale qu'il voudrait que vous compreniez, c'est qu'un robot n'est pas seulement un robot humanoïde, mais c'est tout type de système qui fonctionne de manière autonome.
Right, so this opens up many opportunities for robotics application. Okay, in the examples I showed you, examples from transportation, self-driving cars, agriculture, industry, manufacturing industry, so many, all right? So many opportunities for robotics in society.
Donc, je vous avais montré des exemples de robots qui font dans le transport, dans l'agriculture, dans la fabrication, l'industrie et bien d'autres.
All right. So I hope that's important. But now, oh wait, sorry. So I want to move us on. The other thing that we did last week was to look at the agricultural robot system, the PARC robot system that we have. I showed you the different sensors. Okay.
Donc, la semaine passée, il avait montré les différents capteurs du robot.
All right, so there are 4 main sensors in the system. There's the RGB camera, okay, typical camera.
Donc, il y a 4 principaux capteurs sur le robot. Donc,
okay.
Le RGB camera.
Those cameras are here and here. They are facing down, okay? So they are facing down.
Donc, vous avez 2 caméras qui regardent vers le bas.
All right,
we have vers le sol.
All right, we have the LiDAR. It's a 2D laser scanner. Okay, so this is the laser scanner. It sends out laser scans all around 360 degrees and is able to measure distance to objects by the reflection of those scans. Okay.
Donc,
So,
vous avez le laser scanner 2D qui permet de mesurer la distance d'un objet par la réflexion des lasers.
all right, so this is a primary one that we use a lot in robotics, especially for mobile robots. It's a very common sensor for mobile robots. And it's primarily used to give the robot a sense of the things that are around it. Okay, so with this, it can tell, oh, what is around me?
Donc, ce capteur est utilisé essentiellement est vraiment beaucoup utilisé dans l'industrie, ce qui permet au robot de savoir qu'est-ce qui se passe dans son environnement, qu'est-ce qui est autour de lui.
All right. And yes, I also mentioned the camera. So we have two types of camera. We have the RGB facing down, and this is what it looks like. This is what the camera view looks like. So when it's on the farm, the camera view would show the crops on the ground. Okay.
Donc, vous avez la caméra RGB. Donc, comme vous pouvez voir sur la gauche, vous avez des images de comment les caméras sont fixées, littéralement. Vous pouvez voir les semences sur le sol.
All right, then we also have another camera here facing forward. This is the camera view. It's very small here, but this is the camera view facing forward. This is the RGB camera view, but then this is also the depth image. Okay, so there's the RGB camera view and the depth image that you can see here.
Donc, vous avez la vue de la caméra RGB et une vue un peu plus de profondeur par rapport à la caméra qui est vers l'avant du robot.
All right, so those are the two camera types. So the RGB facing down and the one facing forward. Okay.
Donc,
Then
vous avez deux types de
also,
caméras, les RGB faisant face au sol et le Z2i caméra qui fait face à qui est sur l'avant du robot.
right. And also we have the GPS. We have the GPS sensor that can give you GPS fix. Usually that would be longitude, latitude, and altitude information. In simulation, we simulate this data, but it can give you the longitude and latitude information of your robot.
Donc là, vous avez aussi sur le robot un GPS. Il est fréquemment utilisé pour trouver la longitude, la latitude et l'altitude. Donc, les informations du GPS vous seront données en simulation.
Right. So so basically, when you have this robot, you have these 4 sensors. The task usually is, how can I use these sensors to understand where I am in the world? And based on that, how can I act in the world? Okay, so I use sensors to understand where I am in the world. And then based on my understanding, how can I act in the world? How can I do something? How can I move somewhere? How can I, move somewhere or grab something? So the robot is acting in the world, right? So the sensors tells the robot where I am in the world, what is around me in the world, and then the robot can use that information to act in the world.
Donc, les capteurs permettent au robot de savoir sa position, qu'est-ce qui est autour de lui et quelles sont les informations qu'il a à comprendre par rapport à la position dans laquelle il se trouve dans le monde.
All right, please feel free to ask questions, anything that we're covering. There's no specific question time, so anytime is question time. Anytime you have a question is question time, so please feel free you can raise your hand, you can ask question in the chat, you can unmute yourself and ask a question, anything is fine.
Donc, sentez-vous libre d'ouvrir votre micro si vous avez une question. Donc, tous les à tout moment, vous pouvez poser des questions, soit en écrivant dans le chat ou en ouvrant votre micro.
All right. Also, we reviewed this, what I call the control cycle for a robot. And this is really very fundamental to robotics, right? You have a sense behavior, you sense the environment using the sensors we just talked about. Based on the sensing information, you need to make sense of the sensor information and use that to think or plan some behavior. And then once you have a plan, you can execute the plan by acting using actuators. Okay, and that will have an impact on the world. After you do that, you sense again, think again and plan, and then act, and then sense again, think and act. So it's a circular thing.
Donc ici, vous avez devant vous une boucle, en fait, une boucle de comment est-ce qu'un robot est censé agir. Vous avez le sens, la réflexion et l'action. Donc pour la première boucle du sens, le robot va analyser son environnement et en fonction de son environnement, il pourra réfléchir, planifier, c'est-à-dire planifier et agir en fonction de ça.
All right. I hope that is clear because that is very important. So the example one that we started working on last week was a simple example. The example was a approach the barn task. Okay, so this is the barn. This is a farm. There's a barn here. And the robot starts far away. And the task is robot should approach the barn and stop when it is 6 meters approximately away from the barn. Okay, so I have this arrow here to show you what 6 meters might look like. The robot should start here and drive onto this point and stop.
Donc l'exemple de la semaine passée, c'est-à-dire l'exemple 1, c'était l'approche de l'étable. C'était la tâche de l'étable. Donc le robot doit être capable de se positionner à 6 mètres avant d'atteindre l'étable.
All right, very good. So we started working on this last week, but I don't know how many people were here from last week also. I want to ask anybody here, how would you go about solving this problem? What is the steps that you would take for the robot to successfully complete the approach barn task?
Selon vous, quelles sont les étapes que le robot devrait suivre pour accomplir la tâche?
Okay, let me just give some more detail. You know the robot start position is around here. You know the barn is around here. Okay, that is what you know. And you have all the sensors I already described to you. You have the camera, GPS, and the LiDAR sensors. How would you solve this problem?
Donc, vous savez que le robot est assez loin de l'étable. Vous avez la caméra, vous avez tous les capteurs. Donc, comment pensez-vous que le robot devrait agir pour atteindre les 6 mètres de l'étable?
Anybody, you can unmute and share any idea you have. Anybody has some idea?
Vous pouvez toujours ouvrir votre micro.
Hello.
Yes, go ahead. Who is that?
Tito.
Tito, yes.
Yeah, good afternoon.
Good afternoon.
So since the start position and end position is already known, I think the important sensor here, the most important sensor for this task would be the LiDAR, because it's going to send laser beams. So basically, at the first task is the first thing is for the robot to start moving, and as it's moving, it's sending out laser beams, and the feedback from the laser beams is telling it, okay, we are this distance, you are this distance, and basically when you get to that distance, you're going to stop. So for a Python code, it's going to be in a while loop with an if statement condition and statements of the laser and the laser readings. So basically, once it gets to the laser, gets to a position where it's close to 6 meters from the barn, it automatically stops.
Awesome, awesome. That is very good, Tito. Thank you.
Donc, il vient d'expliquer que selon lui, la première action que le robot devrait faire, c'est de se déplacer et envoyer, et le capteur LiDAR devrait être capable d'envoyer des rayons laser sur les tables afin que le robot puisse savoir à quelle distance il se trouve. Et si on considère cela dans un code Python, on devrait utiliser la loupe if et while.
That was very good, Andrea. Awesome. All right, so yeah, that's a great contribution, Tito. I think that is spot on. Does anybody have any maybe similar or a different approach? You know, the thing with robotics is that you can always solve the same problem with multiple approaches, right? Multiple approaches. So does anybody have a similar or maybe slightly different or completely different approach? I just want to give one other person a chance to share what they are thinking.
Est-ce que quelqu'un d'autre aurait une autre approche par rapport à la résolution du problème?
All right, Samuel, go ahead.
Yeah, so it's quite similar to what Tito said. So I'll be using the RGB camera or the Z2i camera. So since the camera is at the front of the robot base, the Z2i camera, so it publishes all the should I say the data, all the point data in cloud. So I feel like the camera can send in the feedback. So just giving the image, oh, you're about approaching a particular object, so it tells the robot to stop. So, but then the laser will be important for there to be like measurement. So that's where I don't know if they could work together. So the laser and the camera works together. So for the measurements, you need the laser and also the camera. I don't know if there's some measurements with the camera too. So, but I think the laser will do the measurement. So Tito ideas, but it's much good for the laser. Yeah.
Very good, very good, very good. So yeah, thank you, Samuel. Andrea, did you catch that?
Donc l'idée du précédent participant était de dire que on aurait besoin de la caméra et du LiDAR, mais que l'idée de Tito était aussi la plus explicite.
All right. So this is a very simple example, actually. And I designed it that way because I want it to be fundamental, very simple, so that you don't need to even think too deeply. Well, not too deeply, but not too complex, okay? This robot only needs to move straight and only needs to know when to stop, okay? It doesn't need to turn left or right. We have positioned the robot in front of the barn so that it doesn't need to rotate left or right. It just needs to move straight and know when is the right time to stop.
Donc, pour cette tâche, il a essayé de faire en sorte que la configuration ne soit pas trop compliquée, c'est-à-dire le robot n'a pas besoin d'aller à gauche ou à droite, mais juste tout droit pour accomplir sa tâche.
Okay. And Same, I think, from what Tito said. He said, okay, the main question here is how can I use my sensors to know when to stop? Okay, and he said, we can use the sensor, the LiDAR, to measure the distance of all the objects around the robot. Okay, all the objects around the robot can be captured by the LiDAR. Okay, and so we can use the LiDAR to know how far is there anything in front of the robot, knowing that the only thing in front of the robot is going to be the barn.
Donc, il a dit qu'il fallait utiliser un LiDAR qui permettait au robot de savoir tout ce qu'il y a autour de lui et afin d'accomplir sa tâche.
All right. And once you can get the right information from the LiDAR, all you need to do, like Tito also mentioned, is to have some kind of condition to say, if the robot has gone below this distance, then stop moving. If not, keep moving towards the barn. Okay, so it's very simple logic.
Donc, après avoir reçu les informations du capteur LiDAR, vous devez être capable de préciser au robot que si telle ou telle situation arrive, fait telle ou telle autre action.
Okay, and in the other case that Samuel mentioned, instead of using LiDAR, or maybe not only LiDAR, you can also use the camera. That, like, again, like I said, there are many, many ways you can solve this. I think from what I understand, what Samuel was saying is that the camera in front of you produces two images, okay? The camera produces two images.
Donc, la caméra vous permet d'avoir deux images, littéralement.
All right, the camera produces an RGB image, just a normal color image that your phone can, your phone would create if you take a picture, an RGB image.
Donc, la caméra vous donnera une image RGB, comme la caméra de votre téléphone.
Right, and by the way, does anybody know what the RGB means? What is RGB?
Est-ce que quelqu'un connaîtrait ce que RGB veut dire?
Because I've used that word many times, or maybe it's not clear to some people. Right, so RGB, if I say something is an RGB image, right, it is the format that an image is stored in. The image is stored in 3 channels, and the red, green, and blue. Okay, the mix of the red, green, and blue in each pixel of your image is what determines what you see. Okay, which is very interesting way of capturing images.
Donc, RGB veut dire rouge, vert et bleu, donc red, green and blue. Et ça vous permet de capturer les images.
All right, so thank you, Tito. So in the computer vision intro workshop, we'll talk more about image processing, image analysis, and whatnot. We'll talk more about RGB images. But for now, just know that RGB image is similar to what you get from your phone. Take a picture of your phone. That is mostly an RGB type image, okay?
Donc, il faut comprendre que le RGB est juste un type de visualisation qui est similaire à celui de votre téléphone.
All right. So that's one type of image you can get from the camera that we are using in the front of the robot. The second type of image is what we call a depth image. Okay, this depth image actually gives you, like the name suggests, depth information of every pixel in the camera image. It gives you a depth information. That means how far away things are for every pixel of data in your image.
Donc, l'autre type de caméra vous donne une information précise de la profondeur de l'environnement
Okay, so
par
what
rapport
we're
à
seeing,
l'image.
all right, so what you're seeing here actually is the depth image, okay, that is maybe being displayed as a point cloud. So this is a depth image from your camera. This is the depth image from your camera, and it's giving you the depth information of all the pixels that are being captured. And that depth information can be used to find out the distance of the barn. You can use that to find out the distance of the barn as you're moving.
Can you repeat, please?
Yeah, so the depth image is what we're seeing on this side, on this view, and you can calculate the distance from the barn using that depth image information.
Donc, ça vous permettra de calculer la distance de profondeur du robot de la ferme.
Yeah, but that is a slightly more complex approach. It's a lot easier to just go ahead and use the LiDAR information. So in this example, we'll use the LiDAR because that is actually what you should use in this kind of problem, as opposed to playing around with point clouds.
Donc, cette caméra est assez complexe à utiliser. Donc, pour cette tâche, le capteur le plus efficace, selon lui, serait d'utiliser le LiDAR.
All right. One advice I'd like to chip in here for everybody, and also for the for general about robotics, is the simplest solution is always the best solution. Okay, simplest solution is always the best solution. Don't make things more complex than they need to be.
Donc, le commentaire qu'il voudrait faire par rapport à cela, c'est utiliser des solutions simples. Ne rendez pas compliqué ce qui peut être fait de la manière la plus simple possible.
Okay, so if you can use a simple solution to solve a problem properly, go ahead that way. Don't try to add more complexity, because more complexity causes more margin for error and reduces your overall robustness. Okay, so always go for the simplest possible solution that solves the problem. All right, that's just a general tip.
Donc, considérez la solution la plus facile. Ça vous permettra de ne pas vous compliquer vous-même la tâche.
All right, so let's move on. I'm glad that we covered the high level of that. We spent a bit more time, but last week we started to write code, and I wanted to move on here. I did a brief introduction to the structure of ROS, okay? I hope that everybody has had a chance to review some of the materials on the website about how to use ROS.
Donc, la semaine passée, on a fait une petite introduction sur ROS. Et donc, il espère que certains d'entre vous ont compris un peu par rapport à ROS.
All right, so ROS uses publishers and subscribers to transfer information, transfer data from different parts of your software stack. Okay, so topics are used to transfer information from publisher to subscriber and whatnot.
Can you summarize, please?
All right, yeah. So in the ROS communication network, you have publishers and subscribers communicating over what we call ROS topics.
Donc, pour ROS, vous avez un publicateur et un suiveur qui vont communiquer par un même thème, ROS.
All right, so let me actually stop sharing here. Let me point you to some of the very important information that you need to have. All right, so I'm just showing you. Okay, so this is our website, course website. You can always change language to French if you prefer. All right.
Donc, c'est le site. Vous pouvez toujours changer les informations, changer la langue.
All right, so what I want to emphasize here is this, okay? Ross on-ramp. We need you to go through these tutorials, okay? We cannot teach Ross enough on the workshop like this. It takes too long, and we cannot do it as well as the people who have done it on these tutorials. These people are experts. So please, for you to be able to actually complete this competition, you need to learn Ross. So we have put some good tutorials here. Please, please go through the tutorials.
Donc, pour avancer efficacement dans la compétition, vous devez apprendre en Ross. Donc, sentez-vous libre d'aller sur le site et de regarder les vidéos de tutoriels qui y sont postées.
Okay, so we say here, we strongly recommend you put in the time to use these resources, okay? Strongly recommend, all right? Very important, very important. What I'm going to talk about today, how we're going to write the code today will be hard for you to understand if you have not gone through these tutorials.
Donc, ça sera un peu compliqué de comprendre le tutoriel d'aujourd'hui si vous n'avez pas au préalable travaillé sur Ross.
All right, the other thing I want to show us is if you come here, you can see the PARC Ag robot and an outline of all the sensors, like I already talked about.
I can see your screen.
You cannot see my screen.
No.
Can other people see my screen?
It's on the screen. The screen is open.
Now it's good.
All right, so what I said was here we can see the Ag robot description of all the sensors, like I already went through with you.
Comme vous pouvez le voir, vous avez les différents types de capteurs.
Okay, and what I actually really want to show is that you can see all the topics that you can use to access the information of the sensor. So this is scan topic. This is left camera, right camera topics. This is Z2. So Z2 for the camera. This is GPS. So the main thing I want you to take away from this is that these are the 4 sensors, and you can use these topics to get the information from the sensors, okay? All these ones.
Donc il a mis des indices de code par rapport à chaque capteur sur cette partie-là, littéralement. Donc, vous pouvez toujours utiliser ces petits topics-là pour avoir des informations sur chaque capteur.
All right. Very good. Any questions about this? I want to move over to now us going back to writing code. So we're going to finish up what we started. Yeah, go ahead.
Est-ce que vous avez des questions? Parce qu'après ça, on va aller sur la partie coding.
All right. We will finish up what we started last week. That is with writing code. So if you have any questions, please feel free to ask now while I just get my environment set up so that we can write code together. And by the way, let me put the link to the GitHub repository here. I put that in the chat, okay? So that is where some of the code for this workshop example is, okay? I put
Donc,
it in the chat.
vous avez dans le chat le lien qui vous permet de rentrer sur le GitHub de la compétition.
All right, any questions? Anybody have any questions? Is
Est-ce que vous
everything
avez des
very clear?
questions?
Okay, looks like we don't have any. Looks like we don't have any questions. All right, I just want to just give me one moment. I'm trying to arrange I can share my screen again and we can go ahead and start writing code together again.
Donc, il va commencer, il va partager son écran dans quelques minutes pour commencer le code.
All right, I think I'm ready. All right, so let me share my screen. Usually when I write code, I have two screens, but I'll have to show you everything I'm doing. So I'll use only one screen. All right, can you see my screen?
No.
It should be showing now.
Yes, we can see your screen.
All right, very good. No, this is.
I still can see it.
You cannot see. I don't know why. It seems like it's slower on your end, Andrea. Not sure why. Can you see it now?
No.
Are you using your phone or something?
Yes, I'm using my phone.
Ah, maybe that might be it. Okay, well, let me try and reshare, and if not, maybe you might need to find an alternative. I will try and reshare again. Okay, so I reshared again. Can somebody let me know if they can see the screen?
Yes, we can see
we
the
can
screen.
see the screen.
All right, good. Andrea, can you see the screen?
I just connected my computer, so I can see the screen now.
All right, yeah, it's probably better to use your computer than your phone. All right, so so this is where we left off from last week. We wrote some of this code already. The main thing I want to highlight here is this control loop.
Donc, la chose principale de laquelle je voudrais parler maintenant, c'est la loupe.
Okay. But before I do that, let me just give you the overview of what the code looks like. Okay, so this is Python code. Oh, what is this? All right, so this is.
Avant de commencer, je vais donner une vision d'ensemble de ce à quoi le code ressemble.
All right, so we're writing our code in Python. Okay, I got this folder from GitHub using the link I shared with you. If you don't know how to do that, let me show you. This is the link. And this is the link I put in the chat. This is the GitHub repository. Okay, there's instruction on how to get this on your computer. It's called cloning. You will run this command and you should be able to get this on your computer as well.
Donc, pour ceux qui n'arriveraient pas à avoir les informations de l'atelier d'aujourd'hui, vous allez rentrer dans le site Et ensuite, vous allez voir, vous descendez, vous verrez Clone the repository et vous allez être capable de copier et de coller dans votre VS Code.
All right. Yes, exactly. VS Code. Now, once you get that, open it up in VS Code. Okay. Now, I'm not going to go into the detail of how we got here from last week because we already did that. I will just continue from where we stopped from last week. Okay. So we have the main function. Main function is the function that runs when you run this Python script. Main function is what runs.
Donc, quand vous allez run le code, la fonction principale avec def main sera la première fonction à fonctionner littéralement.
All right, and in the main function, there are some things we are doing to set up, just a few setup things. Very simple. We are just initializing the node, and then we are setting some the control frequency, meaning how fast we should be moving in our control loop.
Donc, vous avez installé littéralement, écrit la contrôle vous avez set la fréquence et le timing, donc ça vous permettra de savoir à quelle vitesse et à en combien de temps est-ce que vous pourrez bouger.
All right, and in the control loop, we are doing essentially what I explained to you. So let me show you here. This is what we're doing. Okay, it's very simple. We are sensing, we are thinking, we are acting. Okay, that's all. Sensing, thinking, acting. So you can see the same thing here. Sense, think, act.
Donc, vous allez juste suivre le même processus que la boucle de fonctionnement du robot, c'est-à-dire sense, think, and act.
All right, so if you look at this conceptually, in the loop, we have said that we want this to operate every 10 times a second, that is 10 hertz. Okay, so 10 hertz, it should run this loop at 10 hertz. All right, that is what we have set it to do. Okay, and so every 10 hertz, it will read sensor information, it will come up with a move command, and it should implement the move command. And then it's to go back and start again. Sense, think, act, go back again, and doing it 10 times per second. That is what we have set up.
Donc, la fréquence a été set à 10. Du coup, vous pourrez, ça va chaque seconde, la loupe se fera 10 fois.
Yeah. This is the simplest way, I think, for you to understand how ROS works. There are other ways that are a bit more efficient than this way, okay? But I wanted to introduce this way for those who have less experience with ROS, because I think this is easier to see, okay? You are sensing, you are thinking, you are acting. Then go back again, sense, think, act, sense, think, act. So this is a simpler way to look at it. But if you are more advanced in ROS, you might know how to avoid having this type of loop.
Donc ça, c'est juste un tutoriel pour montrer aux gens qui n'ont pas l'habitude d'écrire des codes, comment cela fonctionne. Mais si vous êtes avancé, vous pouvez toujours trouver d'autres moyens pour présenter votre code.
All right, so again, as usual, if you have questions, feel free to ask them. The way you learn is by asking questions. So if there's something that's not clear, please don't just be a spectator, ask questions. So we have written some of the functions. Go ahead.
S'il y a quelque chose qui n'est pas clair, donc vous pouvez toujours poser des questions, écrire dans le chat ou désactiver votre micro. Activer votre micro.
All right. So so it's usually a good thing to outline what your outline what your functions could look like before you actually write the functions. Okay, so we say, okay, this function is going to be called this, it should output this. This function will have this, maybe to take some argument, it will take some value, and it's also return some value. This function should take some value and do something. Okay, and actually I have not written the code for some of those functions yet.
Donc, cela vous permettra d'avoir une vue un peu plus élargie de ce que vous êtes censé mettre dans votre code, c'est-à-dire sense, take and plan. Donc, comme vous pouvez voir, il y a plusieurs def qu'il a eu à définir. Il n'a pas encore écrit à l'intérieur, mais au moins il sait déjà qu'est-ce qu'il a besoin de coder.
All right. So that's generally a good way to go about it. But last week we wrote out our sensor LiDAR function. The sensor LiDAR function uses this ROS function to subscribe temporarily to this topic that I showed you that gives the data of the laser scanner. Okay, so this function does one simple thing. It collects one set of data from the laser scanner and puts it into this variable. Okay, so it processes laser scanner topic and puts it into here one time, that's all.
Donc, cette fonction vous permet, donc la semaine passée, nous avons principalement codé sur le capteur LiDAR, et cette fonction vous permettait d'avoir en quelque sorte des informations relatives à ce que le capteur pouvait capter.
All right, and then in normal fashion, we are subscribing, we are returning that value from the function here. So that's what we have here. And what I showed you last week is that I tried to print what that data looks like. Okay, using this expression, we can print that data.
Donc, en utilisant print, il a essayé de vous montrer en fait qu'est-ce qui se passe lorsque vous mettez les codes qui ont été écrits précédemment.
All right, so now we are going to run the code like we just so far for what we have. You need two terminals to run the code. The first one is to run the...
Donc, vous aurez besoin de deux terminaux pour pouvoir lire le code.
The first one runs the launch file. Okay. The launch, the information is again in the chat, is here. This is what I just ran, this command. Okay, example 1.launch. That is what I ran.
Donc, la commande qu'il a lancée, c'est celle que vous pouvez trouver sur le site GitHub. C'est pour le premier terminal.
All right, and this is what you should see in Gazebo. Okay, so this is the robot, this is the barn that we are trying to track.
Donc, normalement, vous devrez avoir le Gazebo qui va vous montrer ce que vous voyez maintenant sur l'écran.
And if you open RViz, RViz is also open, you can see this is, like I mentioned, this is depth image. And these small red dots are actually the data from the 2D laser scanner.
Donc, les petits points rouges que vous pouvez voir sont les informations du laser. Et après avoir joué le code, vous verrez aussi que RViz va s'ouvrir.
So one thing you can do is to actually increase the size of the points of the laser scan so that you can see it better. So I can increase it to 0.1 and see it becomes larger, okay?
Donc, il va augmenter la taille des petits points du laser pour que vous puissiez les voir un peu plus clairs.
All right, so you can see that the laser can sense this barn in front of it. You can also sense some things here. These trees, this tree and this tree. You can see the two trees. That's this thing here and this thing here. And you can also see the barn.
Donc, les lasers peuvent détecter les tables et les arbres autour.
Okay, so that is interesting because now we can just try to process that data, okay? So let us go ahead and run the code that we have.
Donc, maintenant, on va jouer le code.
The code we have is in the file name example1_basic.py, okay? So you run it like this.
Donc le code que vous allez introduire dans votre terminal est celui que vous avez écrit dans le example 1.
All right, so you use this structure. ROS run is the command you're asking it to use to run. You tell it the name of the package and then the name of the file.
Donc pour pouvoir jouer votre code, vous allez écrire le nom du package et celui du file, donc example 1 basic.
All right, and so I ran that and it is printing the scan data, which is a lot of data actually.
Donc ça va vous montrer toutes les données relatives au scan.
All right, so this is the beginning of each scan data. It has so many information, okay? It has a lot of information. One of the important things that you need to get used to when you are working in ROS is to understand the data types or data structures, okay? So this sensor information has this particular data structure, okay? So the sensor outputs information in this particular data structure. So you need to understand how this data structure looks like.
Donc, quelque chose de particulier avec ROS, c'est que vous devez être capable de connaître les différents types de données.
Okay, it's very simple to find information. You can always search online. For example, you can just, if you don't really know what it is, you can go to laser scan. This is how I usually do it. Laser scan ROS, for example. And you can find the documentation of the laser scanner type online.
Donc, si vous ne savez pas comment identifier les données, les types de données, vous pouvez toujours faire une recherche Google en mettant le nom du capteur et spécifier ROS.
For some reason, my internet is slow. Okay, there we go. All right, so this is what the data looks like. This is what the data structure looks like. All right, there are different entries of data, and you can read all of this. It all makes sense. The minimum angle, increment of the angles, because remember it is a 360, and I think in our case it's 360 degrees, so it will be from start angle to end angle will be 360 degrees. What we really care about is the range.
Donc, ce qui nous importe le plus dans cette recherche, c'est le range.
All right, the range will tell us the position in meters of each ray, okay? So that is what we really need to understand the distance, all right? And that'll be in meters, okay? So once we have this.
Donc, le range vous permettra d'avoir les informations en mètres où se positionne chacun des objets autour du robot.
All right, so if we come back to look at what we got, okay, you can see angle minimum is minus 3.14. So in ROS, generally we use radians to represent angles, not degrees. okay? We use radians instead of degrees. So this is minus 180 degrees, and this is 180 degrees, right? Because this is pi. This is the value of pi. So this is 180 degrees, this is minus 180 degrees. And then if you add them together, it is 360 degrees, right? Which is 2 pi.
Donc, pour les angles minimum et les angles maximum, c'est la valeur de pi, donc 3,14. Et si vous additionnez les deux, vous aurez le 360. Donc, Ross n'utilise pas de degrés, mais utilise des radians.
Okay, and if you come here to look at the ranges, you will see that it is a list of values. So this this bracket shows there's a list. The list is a long list. It's starting here and it is ending here. So this is the entire list. List of values. Most of these values are inf. Go ahead.
Lorsque vous voyez des petites parenthèses comme ça, des crochets, vous savez que c'est une liste.
All right, and most of the values in the list are INF, which means infinity, meaning that it was not able to actually return any actual value. It's maybe beyond the reading of either beyond or yes, essentially beyond the range of the sensor. Okay, so beyond the range of the sensor, it will give you an infinity value. So if you see infinity value, it means that that particular at that angle, there was nothing sensed within the range of the sensor. Okay.
Donc, si vous voyez INF, cela veut dire infinity. Cela veut dire infini. Donc, autour du robot, il n'y a pas, c'est-à-dire la portée du capteur n'a pas pu capter au-delà de... Yeah.
All right, so that is just general thing. When you are using any sensor, you need to understand what the data structure of the sensor is, and so that you can then know how to manipulate the data that you get. Okay, so I just wanted to show you that.
You can go ahead.
All right, so then you get the scan data. Okay, scan data comes from, let me close Gazebo so I can. All right, so we have defined what scan data is. We can see what the data structure for this variable would be. Now this is going into think function. Okay, it's going into the think function. Now we need to write what the think function is.
Donc maintenant on va commencer à écrire la fonction think.
All right, so now let's think about what we need to do in the think function. Okay, the think function gets as input the raw laser scan data, but what do we really care about? The laser scan data gives us 360 degree range, but what do we really care about? Does anybody have an idea? What range do we really care about?
Donc, quel est le range que nous devons considérer par rapport au scanner?
Good afternoon, everyone.
Good afternoon.
Yeah, so it's afternoon here in Nigeria. So I think we should be looking at the range around 180 because that's what's in front of us.
Yes. Thank you very much, Usman. That is very correct. So let me go back up here. I don't know if this is the best image to use. Yeah, let me use this image. Okay, so this is the direction of the robot. Let me make this larger. Oh no. Sorry, I'm trying to draw here, but this size is too small. Okay, all right. So this is the heading of the robot. This is straight for the robot, okay? And this is 360 degrees around the robot. So the LiDAR is actually giving 360 degrees around the robot on a plane, okay? It's like Usman correctly said, from what we have defined, this would be 180 degrees, okay? If we, this angle forward facing the robot would be 180 degrees. All right, so we can see how this lapping here is 360. You know, the 2 pi of a circle is 360 degrees, and the forward facing direction would be about 180 degrees, where you have 180 degrees on this end and minus 180 degrees on the other end. Okay, so you have from 0 minus 180, 0 to 180, and then 180 to 360 degrees. All right, so to summarize that for Andrea, the main thing is to identify that the angle in front of the robot is 180 degrees, like Usman said. So 180 degrees is also equal to 3.142, that is pi, like I mentioned.
Donc, l'angle, la portée angulaire devant le robot est de 180 degrés.
So let me see if I can show you. Let me see if I can show you that again. Okay, so we had, oh, not this one. Right, so from here, we have the minimum angle to be minus 180 degrees, the maximum angle to be minimum angle to be minus 180 degrees, the maximum angle to be oh wait, is it actually I might actually be wrong. Yeah, it should be 0. Yeah, right. Summer, I think you're right. So I apologize for that. I think let me redraw this again. Let me get my annotation. So let me redraw this.
Alors, la portée angulaire n'est pas de 180, mais de 0.
So let me draw the robot. Okay, so let me draw the robot. Okay, so I'm going to draw the robot. This is the robot. The robot is, this is X on the robot. Usually it is the X direction of the robot. This is the Y direction of the robot. Okay. And usually when you are measuring angles, right, you take angles. So let's say this is the heading of the robot, okay? So the heading of the robot will go from, if this would be the 0 angle, okay? So it would be minus 180 to 0, and 0, you can say maybe to like 180. Something like that. So so this will actually be, this would be the 0 point. So if you have 360 points or data points, potentially, about the center of the robot was where you would have, I'm sorry, about the center of this range value is where you would have the forward position of the robot. So you can see some of that data here. If you look over here, you can see some values here. Some values here, 15 point something, 15 point something. That is about the middle point of this list. Okay, that is where you're about the 0 point where you are looking. Okay, so there are a few things we can always test this experimentally, right? We can always check with we can plot the data and actually see, not plot, but we can estimate from the data and see. So let's try and do that. But not just to give you some general idea of how this is set up. Okay, so yeah, thank you. I don't know who that was on the chat now that made that correction. Thank you for making that correction for me. All right, so let us.
Donc,
just...
dépendamment de la direction du robot. Donc, dans les commentaires, il y a dit si le robot fait face à l'étable verticalement, le degré, la portée angulaire devrait être de 0 degré.
All right, so I'll just do some experiment here and say, okay, what is the number of points that we are getting from from the data? It can be, okay, scan data dot ranges. We can find the length of that. Okay, that'll give us a number of points, and we can print the number of points. Okay, so we can print the number of points. All right, so let's see. So that gives an idea of how large that range value is actually. So let me run that in the code. Oh, I need to run this up first. Okay, so gazebo comes up. All right, so clear this actually. Oh. Maybe too many things printing. All right, so apparently we have the length of the range is 400. The length of the range is, why is this not showing? All right, so the length of the range is, looks like this is, no. All right, so the length of the range is, like we saw up here, is 400. Let me run that again so you can see. Okay, so the length of the range that we are seeing is 4. That's the number of points that we are getting from the range of the scan data is 400 points. So we're getting 400 points. Okay, and that is going from minus 180 past 0 to 180. Okay, so minus 180 past 0 to 180. And that is broken down into 400 points. Okay. And that corresponds to, I think that corresponds to what the angle increment is. The angle increment here will determine, you know, the distance between each degree to tell you, you know, how do you break down this range from minimum to maximum. All right, so, but this is, there's a lot of details. I don't need to get into too many of the details, just the main high level ideas. Okay, so anyways, we have 400 points, and now we can decide which points we want. Okay, we know that we want the range. Okay, we know that we are going from minus 180 to 180. Okay, And we know that the robot is at 0. And we know that minus 180 to 180 has 400 points. Okay. So we can think that 0 points would probably be 0 will be at around midway, right? So midway would be around 200, okay? Because it's going to go from minus 180 to 180, and 0 is about midway of that. And so if it goes from 0 to 400, it would be around 200. Okay? Do we still have Andrea?
Yes, but most of the words you said, I don't understand, so.
Okay. You said most of the what?
The words.
The words. Okay, okay. You mean like technical words? Is that what you mean?
Yeah.
Okay. I mean, if you don't understand, can you just ask me to repeat? Okay, so that you don't. All right.
Okay.
Yeah. All right. So to summarize what I've been saying is that we need to find what region of the scan we need to extract. Okay, the scan has 360 range. Okay, and that is equal in 400 points. Okay, we already checked the number of points.
Donc, vous avez besoin de déterminer la portée sur laquelle vous allez travailler pour déterminer la suite du code. Voilà pourquoi vous avez 4 hashtags. Donc, le moins 180 qui vous précise en fait les différents angles maximum et minimum et l'angle. Et ensuite, vous avez la longueur d'exposition au radar qui est de 400. Et le dernier point, c'est le range minimum, c'est-à-dire celui de 200.
All right, thank you. I'm sorry, forgive my drawing. Usually I draw better than this in real life. But anyway, this is 360, this is 0 degrees. Okay, so this is probably around the 200. This is 0 degrees, and that's about 200, 0.200, okay. Go ahead, Andrea. So this is 0 degrees, and this is about 0.200.
Donc, vous avez 0 degré. Donc, on peut considérer ça comme 200 mètres.
All right. So what we really want is to extract the data around close to 0 degrees. Okay, we don't want to take only one point in 0 degrees. We want to take a bunch of points around 0 degrees so we can actually see what's mostly in front of us. Okay, so something like that.
On va prendre un bon nombre de points autour de 0 degré.
All right, so if that is what we want to do, I'm going to get this off. We can say, okay, we can call this forward range, and we can split our list and say, okay, we want to take from 190 to 210. Okay, so that gives us 20 points that center around 200. Okay.
Donc, il a déterminé un range vers l'avant, donc un certain nombre de points qu'il voudrait voir d'une part et d'autre des 200.
Okay, and then now we can print this forward range and see what that looks like. Okay, so we can print forward range. So this is just choosing 20 points that center around 0. So that's from 190 to 210.
Donc, de 190 à 210, autour de 0.
All right, and this is what we This is what we are getting. So if you see, this is what we get. We get this, okay, so 15.7, 15.7 to 15.6. I think that makes sense if you're looking at currently how far away the robot is from the wall, okay?
Donc, après calcul, quand vous regardez dans le terminal, c'est assez approximatif.
So right now, this is this distance from this red dots to the robot. What is the distance that we are measuring? Okay, we're taking that distance, and that's distance we care about.
Donc, on considère la distance entre les tables et le robot. Donc, celle qui a la distance que vous pouvez voir highlighted dans l'image.
All right. So in the interest of time, we'll move on. One thing that you might actually need to do is to try to filter the data, okay? In case they're inf, you know, sometimes they are INF, like I showed you. Let's say we do 170 to 220. You might find that we might see some inf data in inf points. So let me see. Oh, right. Oh.
You activate the print.
Right, yes, sir. I didn't print. Yes. All right. So depending on the range that you take, in this particular example, you see I increased the range, you're getting infinity values. So be careful about that because you cannot really work with these infinity values. I just wanted to show you that as a scenario. Okay. So
Donc, vous ne considérez pas les valeurs infinies.
Yeah, so if you're actually working on this, and this is a very simple example, so we can directly hard code some of these things. But if you're ever doing that, you need to filter the data to remove any of the infs. Okay, I will not do that for us. But this is a simple way you can think about looping through. How you could do that is you can loop through the data and see if anything is inf, remove it from the list. Okay, that could be a simple thing to do.
Can you repeat?
Well, the next thing that we need to do is that we need to get an estimate of the distance to the wall. Okay, that's really what we care about. We care about distance to the wall. Okay, so one thing that we can do is that we can compute an average value. Okay, distance to wall measurement. Okay, we can compute some kind of average distance to wall measurement. Okay.
Donc, ce que nous considérons réellement, c'est nous devons estimer aussi la distance entre le mur et le robot.
Let me just shut down Gazebo where we type. Okay, so simple, we can calculate a simple you can do sum over length. I can give you a value for distance. Okay, this should work in some cases, but this should mostly work. So you can see why it's important to filter, because if you are summing a list that has an infinity, then that doesn't work, right? You cannot really, the sum of infinity is infinity. Infinity divided by anything is infinity. So you need to make sure you don't have any infinity value in your forward range. Okay.
Donc, dans le range, dans le bracket, c'est-à-dire le 190-210 que vous avez déterminé, vous devez faire attention à ne pas considérer d'infini. Sinon, lorsque vous allez écrire la formule, c'est-à-dire somme sur longueur, vous aurez toujours infini comme résultat.
All right, so, but this is not robust code, but I think it should be okay as a demonstration for us to see. And now I can try to print just the distance value, okay? Distance to the wall.
Donc, il va essayer de print ce qu'il vient d'écrire dans le code, c'est-à-dire l'application de la formule.
All right, and we should have, okay, so the average value there is 15.6, okay, which I think is reasonable. Distance to this wall.
Donc, comme vous pouvez le voir, la distance est de 15,62.
All right, so the next thing we can think about doing, and remember there are many ways you can go about this, but you can say, okay, have a condition, okay? Remember, like Tito mentioned, we need to have a condition if the distance to the wall is above some threshold, okay? The threshold we have set is 6 meters, okay? Then you need to like move forward. Okay, that is what we want. If it is above 6 meters, move forward. If it is less than 6 meters, stop. Right?
Donc, vous pouvez toujours définir une condition pour préciser au robot que si c'est au-dessus de 6 mètres, il doit stopper.
So let me I can call this approach threshold is 6.0. Okay, this is in meters. And I can have a condition. If the distance to wall is greater than approach threshold, okay, we can say something like a move flag is true, okay. And else, move flag is false, okay? So this could be something you could do. This is just to give you a simplified approach to how you can solve this problem. Okay, so
Donc,
the thing...
Vous pouvez dire au robot que si la distance du mur qui était de 15,62 est supérieure aux 6 mètres déterminés, vous pouvez dire true ou false, donc mettre une condition loop. Boolean une condition.
All right. So it's just given that, and we can see what we return here is the move flag. Okay. So if we come down to what our main function is again, maybe I'll change this to move command. You can still call it move command, but let's say we call it move flag. And act as move flag. Okay. This is by no means how you should do this. You can do it in many ways. I just want to show one maybe simple way.
Donc, il a fermé la condition précédente par rapport à think. Et voilà.
All right, so if we just go about what is the framework here, the sense lidar again gives out the scan data for all scan data. Okay, the think takes the scan data, processes it, and tells you whether you should move or not move.
Donc, les données qui ont été prélevées sur le lidar seront ces mêmes données-là qui seront analysées par dans la session think. Et ensuite, je pense qu'on passera à Act.
Right, thank you. Oh, yeah, there's a question in the chat, Tito. Yes. So Tito's question is, so you need to create a new list of ranges disregarding the inf values. Yes, so that will be one way to do it. You can create a new, you can create a new list that you make sure that you are checking that every element in that list is not an inf, or there could be some existing Python code, some Python functions that actually can filter directly. So there are different ways you can do it. You can write your own simple 3 lines of code to loop through your list and remove all the infinite values. But yeah, that is what you should do. Okay. All right. So I think the summary of what I was saying is that, yes, just saying yes to Tito's question. Tito's question was that for the filter, do we need to create a new list where you remove all the inf values? And the answer is yes.
Ok, donc pour les données du filtre, vous pouvez retirer toutes les valeurs infinies.
All right, very good, very good. So I think this looks good. Now we can move on to the act. Okay, so act, remember, is the last part. Act is what we use to actually drive the robot. Okay, so act takes in the move flag. Okay.
Donc on va passer à la fonction act. Donc on repart au début pour pouvoir déterminer toutes les actions relatives au mouvement du robot.
Now, one thing I have not included here, I need to introduce to you now, is the idea of the publisher. So we need to create a publisher to send velocity commands to the robot. Okay, remember I talked about how Ross uses subscribers and publishers. So now we need a publisher that we use to send velocity commands to the robot. Okay, so we need to create a publisher that we will use to send velocity commands to the robot.
Donc vous allez établir un publisher qui va permettre d'envoyer les données, les commandes de vitesse au robot.
So this is a standard structure. Once you go to the tutorials, you can get familiar with the structure of the publisher. Okay, this is the topic. Command value is the topic that you use. Okay, so command value is the topic. Twist is the message type. Again, we need to include that message type.
Donc vous devez inclure le message.
Okay, if you don't know what twist is as a message type,
vous devez prédéfinir la géométrie du message.
You can always come here and search, actually. Okay, this is one good way to find it. There are many other ways. You can also search on your terminal, but this is one way to go. So this is the twist. Twist is just a standard format of defining velocities in free space. Okay, that is the standard format for defining velocities in free space. So there are 2 types of velocity. There's linear velocity and angular velocity. Okay.
Donc twist, c'est le standard, c'est un standard par rapport à la mesure de la vélocité. Et il y a 2 types de vitesse, donc la vitesse linéaire et la vitesse angulaire.
Right. Yes, so so to the topic, yes. So to the topic is command vel. Okay, so this is the topic for this is the topic that the robot is going to be receiving velocity commands from. That's the topic name. Okay, that's the name. I think I may need to put a / there. That is the topic name, and this is the message type for the topic twist. All right. So we need to pass this object All right, so we need to pass this object that we just created into the act function. That's why I just created it there, because we need it inside here. Okay. All right, so ultimately,
Donc,
what we're going to do, go ahead.
donc il a inséré l'initialisation, il a inséré le message précédemment défini dans la partie acte.
So we can create a new twist object. Okay, we can call it whatever we want. Let's say robot velocity, you can say. Okay.
Donc, vous pouvez écrire de la manière dont vous voulez, mais on va juste définir un nouveau twist.
Okay, then we can set the nominal forward velocity. Okay.
Et après, vous pourrez
Let's see.
déterminer une vitesse nominale
Second.
pour le robot.
Okay, the robot should be moving 0.5 per second. All right, so now our condition again. So if the move flag is true, then move robot. Okay. All right, so have if
Donc
move
ensuite,
flag.
vous pouvez déterminer une condition selon laquelle si la condition move flag est vraie, le robot devra bouger.
All right. And we can make some message that says robots moving, something like this. Okay, this is
Ensuite, vous
just
pouvez définir un message pour préciser que le robot est en mouvement lorsque la condition est respectée.
right. If it is not, if the move flag is false from the previous function, then this should be set to 0. Okay, the velocity should be set to 0. Forward velocity. Okay.
Donc, s'il s'avère que la condition move flag ne soit pas vraie, le robot devra stopper.
All right.
Donc, la vélocité sera de 0. Go ahead.
So then we can publish velocity, essentially. All right, so we can publish the velocity using this function we already wrote. Okay, publish velocity. And then I'm also adding a return variable because I want this to return a simple variable called message, just the message that message is whether it is moving or it is stopped, just for us to see.
Donc, après, vous pouvez ajouter une fonction return pour pouvoir avoir des informations sur le mouvement du robot.
All right, so I think let me just review what we did in ACT. Okay, let me review this with you. We created a new twist object. All right. Yeah, go ahead,
Donc,
Andrea.
dans la partie Act, on a créé un nouveau twist.
All right, we decided that we want the robot to be moving at 0.5 meters per second. So we set that
Et
value.
ensuite, On a déterminé la vitesse de mouvement du robot à 0,5 mètres par seconde.
Then we are saying that if the move flag that we define in the think function is true, then set the robot velocity linear, that's the forward linear velocity, to be what we already said, forward velocity. If not, set that forward velocity to 0. That means stop.
Donc, ensuite, vous avez défini ensuite, vous définissez la condition selon laquelle si le move flag n'est pas respecté, ben, la vitesse linéaire du robot sera de 0, ou dans le cas où il est respecté, le robot devra bouger selon la valeur de la vélocité qui est de 0,5 mètres par seconde.
And then finally, we just take that value that we have created and publish it. That means send it to the robot. This is what we use to send that command to the robot.
Ensuite, maintenant, les valeurs collectées lors des précédentes actions, des précédentes conditions seront envoyées directement au robot par la publish velocity.
All right, so let us see. Let's see whether what we have works. We might have some bug that we can fix, but let us see. And I think once we are done there, I'll open for any questions people have, and then we will call it a day today.
Mais ensuite, vous pouvez ouvrir le terminal et pour vérifier votre code.
All right, so let me launch this again. Okay, that is launching. Let's zoom out so we can see the robot properly. Okay, so I'm going to run the function again. We'll see. All right, so the robot is moving and shows you, I'm printing out the distance to the wall. I'm printing moving at the time. And let's see whether the robot will stop when this distance to the wall goes below 6. That's what we expect it to do, right?
Donc, comme vous
All right.
pouvez le voir, en train de tester le code. On va voir qu'est-ce qui se passe si le robot arrive dans une distance similaire à 6.
All right, so we can see we're about 5.9, and we can see robot stopped. That is the message we are publishing now. Robot stopped. So remember, before we were here, robot moving. And then once, based on what we have in the think place, once they went below the below the threshold, it switched to false. Once we have false there, the robot will no longer send forward velocity. The forward velocity becomes 0 and it will become stopped. Okay?
Donc, comme vous pouvez le voir, la condition précédente qui a été définie a été respectée. Donc, vous voyez, dans le terminal, c'est écrit robot stopped.
All right, so I hope that this at least gives you, especially for some of us that are newer to ROS and Gazebo and robotics, this could give you some general idea. I know that there are many technical details that I did not spend time to explain. I need you to maybe watch some of those tutorials I showed you from ROS so that you can understand some of these data structures that you have to use. But the main thing is that I want you to get this main loop idea, okay? It's a simple idea that you will sense, that is to collect data from your sensors. You would think, process that data and come up with a plan. And then based on that, you will act, meaning that you would command your actuators. In our case, it is in the motors, we give the motors a command velocity. Okay, and that's really the fundamental concept around mobile robots: sensing, thinking, and acting. Okay.
Donc, si vous voulez respecter les conditions fondamentales d'un robot, vous pouvez suivre spécifiquement ce qu'il a fait, c'est-à-dire suivre la main function, la fonction principale, c'est-à-dire en divisant les différents capteurs entre sense, think et act.
Yeah, I want to show you one experiment before we close today. If you notice here, we are sampling at what frequency? I think that's an important thing for you to notice. You see, this is, I'm printing out the time, seconds. I'm printing out the seconds here, okay? So this is 89 seconds, 0.54, 89 seconds, 0.64. So that's how many seconds? 0.1 seconds, right? 0.1 seconds. So every 0.1 seconds, it is going through this loop. And that is because we set 10 hertz, okay? That is because we set 10 hertz.
Donc, si vous regardez dans le terminal, vous pourrez avoir une idée du timing, c'est-à-dire ça part de 0.1 à chaque fois. C'est à cause du nombre de fréquences que vous avez déterminé.
Let me do something. Let's say we say that we want a smaller frequency, 0.5 hertz. 0.5 hertz is how many seconds? Does anybody want to give it a try? How many seconds is 0.5 hertz?
Combien de secondes fait 0.5?
2 seconds.
2 seconds, yes, thank you. So let us see how the robot will behave if we're only doing our control loop in 2-second interval. Let's see how our robot will do, okay?
Donc, on va changer la fréquence et voir ce que ça donne.
Yes. So you can see that every 2 seconds that it is plotting, it is printing out the data. Every 2 seconds,
Donc, vous verrez que chaque 2 secondes, les données seront reportées dans le terminal.
Okay. All right. So you will notice it stopped, but see, it stopped at 5.3. We're supposed to stop at 6, or we stopped at 5.3. Why? Why did it stop at 5.3?
Pourquoi, selon vous, le robot s'est arrêté à 5,3?
Or maybe not 5.3, but at least the first time it stopped was 5.4. Yeah, so this one, 5.4 instead of 6. Anybody have any idea?
Est-ce que quelqu'un aurait une réponse?
Any idea? That will be the last word for today. Any idea on this? And then we will close it. This is an important idea in robotics because of the reduced time. Can you explain what you mean, Tito? Why because of the reduced time? Okay. Anybody want to help Tito out? That is right, because of the reduced time. Why exactly?
Okay, so Initially, the frequency was set to 0.1 seconds, that is 10 hertz. So meaning
Yeah.
it's getting data like I don't really know how to put it though, but let me try. Well, with the time being reduced, the amount of data is going to collect is going to be more
Yes.
for acting. So unlike when it's increased, like the 10 hertz, it collects data at each point. So the data is minimized and then it can act with the immediate data given. But accumulating data over a period of time and then acting, accumulating. So there's like a range of data it accumulates at those intervals. So that's why it stopped at 5.3 instead of 6.
Right, right. So that's right. Thank you for that. Just to summarize what was said, it is almost as if you think about this experiment. Imagine you are walking from your chair to your door, okay? And you stand up and you walk to your door, okay? But instead of doing it normally, what you do is you put your hand over your face, over your eyes, and only remove your hand every 2 seconds, okay? So you walk, put your hand over your face, walk for 2 seconds, open your eyes, and then look at where you are. Oh, where is the door? Okay, the door is forward. Okay, then you walk forward. But then you cover your eyes, and then you walk again, and then you open your eyes. What you might find is that you are only sampling, you're only getting information about what you need to do for 2 seconds, and during those 2 seconds, you don't know what's happening in the world, okay? You don't know what's happening. For 2 seconds, you are following the think plan that you got 2 seconds, 2 seconds before, okay? So why it is overlapping here is that the last time that the robots processed the distance to the wall, it was 6.3. So the robot said, well, I should keep moving, right? Because 6.3 is more than 6. But then it assumed this 6.3 value for 2 whole seconds. And based on our 0.5 meters per second speed, 0.5 meters per second times 2 seconds is 1 meter, about right? Approximately 1 meter. So it will actually move over 1 meter before checking again what is the distance. By the time it checked the distance, it has already overpassed the 6.0 threshold. And then it now checked, oh, okay, I should stop. Let me stop now. All right. So this is just the importance of having fast sampling rate, fast control frequency. Otherwise, you will not be able to know how your world is changing around you. Okay, so that's just one way I want to end this session, for you to have an appreciation of that concept. Let me show you here. This is the control frequency. How fast you can set this control frequency is very important for your sensing, thinking, and your acting, okay? Because this is almost a discrete system, essentially. All right, it's a discrete system. In one control loop, everything is fixed. Okay, and you need to be able to move that, you need to be able to do multiple control loops as fast as possible so you can get more data. All right, so let me summarize that for the interest of French listeners. And Jai, I don't know, maybe you got some of it, but let me just summarize it. The reason is because of the, because this is a moving system, and the last time that you collected data to know the distance was 6.3, and you said, okay, let me move, but then you wait for a long time before you collect data again, and by the time you collect the next data, you've already overstepped your threshold. That is the reason why overstepped.
Donc, pourquoi est-ce que le robot s'est arrêté à 6 secondes? C'est parce que le temps de collection de données a été plus long que prévu. Donc, à chaque fois que le robot doit collecter des données, il les collecte et avance à l'aveugle. Donc, au moment où il reprend à collecter des données, il remarque qu'il a déjà dépassé la limite qui lui était donnée.
All right, thank you. So that is the end. I will upload this file, this example basic, to GitHub so that you can all use it. I'm going to stop sharing.